In this presentation on dynamic modeling, we will give you an overview of the dynamic solvers available in CivilStorm and SewerGEMS, and we'll show you some situations where the use of a dynamic solver is recommended. For a detailed description of dynamic modeling, as well as stormwater theory, design guidance, and hydraulic modeling techniques, we recommend this book from the Bentley Institute Press, which just released its second edition in 2020. Here's a preview of some pages of the book that cover flow routing methods. Now, to model open channel flow, the engineer must know the flow conditions. We're going to go over the most common types. Here you're looking at steady uniform flow. Steady means that the flow remains constant over time at any given point in the channel. And steady uniform means that not only the flow stays constant, the depth and velocity also remain constant. In uniform flow, the depth of flow is called normal depth. And when flow is at normal depth, steady state equations are acceptable, and friction losses can be calculated using equations like Manning's or Chessy's. In this particular situation, a dynamic model is not needed unless you had changes that were rapidly occurring. But we're assuming they're not because we're saying the assumption of a steady is that the flow stays the same over time. You could solve the network by hand if you had the time. You could use a program like Bentley Flowmaster for a single element, or you can use a steady state solver. Here's a steady situation, but now it's varied flow. So with steady varied flow, flow remains constant over time. But as you can see in the picture, depth and velocity change along the length of the channel. Why could that be? It could be a result of a change in channel geometry. So we'd be talking about non-prismatic channels. It could also be that the slope is changing along that length of channel, or it could be influenced by a flow control. Now, because of the variable channel geometry or the presence of flow controls, the data required for gradually varied flow analysis are considerably more complex than for the previous case of uniform flow analysis. Now, in this situation, you still don't need a dynamic model. And doing a steady state simulation with a gradually varied flow solver is a good choice. Dynamic solvers only apply to simulations over time due to the nature of differential equations. So you don't really use them for steady state simulations. Okay, here we're looking at unsteady flow. Unsteady flow occurs when, as you see here, flow changes over time. So when we look at unsteady flow, we're always looking at flow changing over time, or hydrographs like the one you're looking at. To do unsteady flow routing calculations, you can use either hydrologic or hydraulic routing methods. So how do you choose? Hydrologic routing is computationally simpler and less data intensive. Hydrologic models analyze flow, and then they use a simplified approximation to account for the hydraulic rate line. SewerCAD, for example, uses convex routing for its extended period simulation. The other routing methods are called hydraulic methods, and they're based on the solution of the Saint Venant partial differential equations. They analyze flow and hydraulic grade simultaneously through the system. The implicit and explicit solvers that are found in CivilStorm and SewerGEMS both use same banana equations. So if you're trying to do unsteady flow analysis, you need to have a computer helping you. This is not something that you would be doing by hand. So although most collection system design is based on steady state hydraulics, so typically you perform some peak flow calculations and you design your systems kind of to be able to handle those peak flows. Steady state hydraulics are very common in the design world. But the reality is that the nature of flow in sewers is unsteady because we have things like storm events, so there is no flow, but then it rains and then we see flow and then it stops raining, no more flow. We also have things like pumps. So when the pump is on, there's flow, and when it's off, there is no flow. So for those normal uh, situations, we know in real life we're dealing with um, unsteady flows. Now, in hydrology, we talk a lot about routing, and routing is a technique that is used to predict the changes in shape of a hydrograph as the water naturally moves through the system. So take a look at the picture here. This first hydrograph, think of it as the inflow hydrograph for a pipe or a channel or even a whole network. So as that flow moves through the system, the hydrograph's shape is going to change. How it changes depends on the size and configuration of the system. For example, if you're only routing this through a short distance or the slope is very steep and it moves rapidly, you'll see that the hydrograph um, flattens a little bit and widens, but not too much. However, if you're routing this over a long distance or the slope is very mild and it takes a long time to move that hydrograph, you're going to end up with something like this. So this process of widening and flattening the curve is known in hydrology as attenuation. Okay, so when I first showed you that animation of unsteady flow, I mentioned that there are different routing methods, right? I mentioned the hydrologic or hydraulic. And I mentioned how the hydrologic is a simplified version. And in those hydrologic models that you see listed here, they analyze the flow using continuity equations, and then they use different approximations. So they kind of get rid of some of the terms in the equations of the same and an equations, and they simplify it to come up with hydraulic rate line or momentum effects. That works for many cases. As I mentioned, SewerCAD gradually varied flow solver uses convex routing. Also, in the swim solver, you can route flows using a kinematic wave routing method. Um, and there are other options as well. Hydraulic methods are based on the solution of the Saint Venant partial differential equations. The way they work is they analyze both flow and hydraulic rate simultaneously, and that's how we get the results. Okay, when we talk about a fully dynamic model, we mean a model that solves the full Saint Venant equations, and here they are. The first equation is the continuity equation. The second one is the momentum equation. And this would be impossible, really, to solve by hand, and that's why we use these computer programs. Now, because we're adding the complexity of the terms, we're adding more variables to the equations that we're solving. These are more precise, but they also can be a little bit more finicky. So we're going to learn about the pros and cons of these models. Um, Also, let me remind you that we assume that flow is one-dimensional in our dynamic models. Okay, to solve those equations that you saw, you need initial conditions and you need boundary conditions, such as tailwater conditions at the outlet. And there are many options in the software to input tailwater conditions. For example, submerged outlets, ponds, or the tide of the ocean. Here you're looking at a free-falling outfall with a flat gate, and that is also an option. So that's what we called a boundary condition. So let's take a look at other situations you will encounter. Here is a similar setup as we had seen before, except we have surcharged flow here. If you have surcharged flow, um, normal depth doesn't exist anymore. So if you have this situation, you can adequately model it using either a gradually varied flow hydrologic method or a fully dynamic method. If surcharging leads to an overflow, as shown here, hydrologic routing requires that the user specify some sort of rating curve in order to model what happens at that overflow. And it's not always easy to determine this rating curve for each manhole or catch basin in your system. Now, if you are using the implicit or explicit solver, they automatically calculate the overflow using the Weir equation. So this is a good situation where you would want to use dynamic solvers. Now, if the surcharge is a result of a downstream backup, then hydrologic routing doesn't work, and it becomes necessary that you use the full dynamic wave equations. Okay, so really for those, the more complex the situation, the more likely it is that you will need to use a dynamic solver. Now let's take a look at each of those individually, the implicit and the explicit. The implicit solver uses a 4-point implicit finite difference solver to find the numerical solutions for the Saint Venant equations. This solver is based on the National Weather Service flood wave model, and this solver tends to be more stable in situations where you have pumping. So there are a lot of pumps in your model, and you need to use dynamic solvers. The implicit solver may be what you need. There's another dynamic solver, which is the explicit solver. This one uses the solver from the EPA SWIM version 5. So the results from using this solver should exactly match the results from SWIM 5. The explicit solver tends to be more stable with ponds or control structures where the flow or the pond elevation changes quickly over multiple time steps. Okay, so either the implicit or the explicit use a Prism slot, like the one you're looking at here, to deal with surcharging and full pipe flow. This is done to avoid discontinuity when you transition between full or partially full flow. And so if you're ever wondering if the dynamic solvers use different equations for the gravity portions or the pressure portions, no, they use the same equations, and this is how that transition between gravity and pressure is handled. One thing that you might encounter, again, because of the complexity of these equations and all the terms that are part of it, you may have stability issues And if you do encounter any issues, like you get a reported continuity error at the end of a run, if it's, less than 5%, you can ignore it. It's not going to be a big deal. But if you get warnings, if you get larger discontinuity errors, here's what to do. Um, most basic tips are avoiding very short pipes or shortening the computation time step or decreasing computation distance. Make sure it's shorter than your shortest pipe and that it's long enough that the model can run in a tolerable time and you're not running this for days. Okay. If you need more assistance with convergence, head over to the Bentley Community's Open Flows Hydraulics and Hydrology Wiki, where you can find a lot more information on these dynamic solvers. Thank you for watching.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.